Hello, everyone. My name is Chad Briddon from the Technical University of Vienna. Today I'm going to be talking about solving for screen scalar fields in arbitrary time evolving systems using SELCIE. So SELCIE is software that me and my collaborators have been working on for the last few years. In its current incarnation, which is publicly available at the GitHub repository, the link is below at the bottom of this slide. So in the current incarnation, it allows you to solve for the chameleon field in arbitrary systems for the static case. So in a few slides, I'll be talking about the chameleon model. In this talk, I'm also going to be talking about the upgrades that hopefully experimentalists find interesting. The main upgrades include there is now the ability to solve for the symmetron field and the promotion to time evolving systems. So both for the chameleon and the symmetron, where not only are you solving for the time evolution, but also the density profiles that govern the solutions can also evolve in time. And you can see how that affects the propagation of the scalar field profiles. This talk is paired with another talk at this conference by my collaborator Andrius. This talk is more about how the code works, whereas his talk is more about how the types of things we've used the code for. So, for example, using it to optimize atom interferometry experiments, looking for the fifth forces induced by these fields. So, in the typical cosmological story, the dark energy that's driving the current expansion rate is due to a cosmological constant, capital lambda. And then the rest of the universe, mostly made up of cold dark matter, but also includes baryonic and radiation. For this talk, those aren't important. What we're interested in is the dark energy component. So the models that we're looking at have a dark energy component that will evolve in time. So the equation of state, for example, of the cosmological constant is fixed at -1 for all times. We're looking at scalar field models where this could potentially evolve over time. One of the reasons that this is of interest is because things like the Hubble tension, depending on which measurements which observables you use to make your measurement. So the divides appears to be indirect early universe and more direct late universe observations. You seem to get two different values. And there's a quite significant there's about a statistical weight behind the fact that there are two values, and it isn't just a statistical fluke that we're not getting the same. Um, and it is this type of observation which could be explained by the dark energy being made up of a time evolving uh, thing, basically. It's not a cosmological constant. So more recently, further evidence for this from the DESI collaboration, where they actually found it's not quite yet at the same statistical relevance of the Hubble tension, but it is about 3 sigma, so still of interest. They found a bias towards an evolving dark energy term. So they don't have, see here on the plot, the dashed line for -1. Rather than having that fixed over time, instead they have the more likely to be an evolving value. So uh, at different times it may be more, different times it may be less. This could, in principle, be in line with a scalar field. So one issue with these types of scalar fields that's going to lead the topic onto the ones that I'm interested in is the fact that if you allow them to couple to matter, that would mean that they would mediate a force between the matter particles in the matter sector. So we'd refer to this as a fifth force because it'd be a new fundamental force. The problem is there have been many experiments looking for these, and we've never observed it. So this will require the coupling to be very weak. An alternative is the models that I'm interested in, where they have a screening mechanism. So these screening mechanisms allowed them to hide themselves depending on the environment. So here I've got two actions. The above action, I have a modified theory of gravity. So instead of the usual Einstein-Hilbert term, there's an additional function A, and there's a scalar degree of freedom. Uh, this class of models also includes f of r models. What's interesting is if we perform a conformal transformation, so the equation in red, where we're rescaling the metric by some function, we can show that this action is equivalent to the bottom action, where uh, the gravitational part is now once again in the Einstein-Hilbert form, but as a consequence, we now have a conformal coupling in the matter sector. So you can think of it as an equivalence between the geodesics of your particles from modified gravity versus where you're considering the contributions of a scalar field that's mediating an extra force. So if you take the variation of that action with respect to phi, you get the equations of motion above. So these are in the Klein-Gordon form, but where now instead of just the bare potential of the field, you get this extra term from the matter sector, giving you this rho. So this is in the non-relativistic limit, and rho is the matter density. And so we have an effective potential on the right-hand side of the first blue boxed equation. So as a specific example, the chameleon, we have a monotonically decreasing potential, so something like 1 over phi to the n, where n is a positive integer. And the extra contribution, so this rho term, means that the effective potential, the dashed line, now has a minimum. And what this means is that the mass of the field is going to depend on that rho. So for the red plot, the minimum is at one value of phi, and it has some mass. For the blue curve, where the density is less, it's less steep, and so the mass is also less. And so what that means is that in denser regions, the Compton wavelength of the field, which is 1 over the mass, is going to be much smaller, and so any fifth forces are going to be suppressed. Whereas in less dense regions, the Compton wavelength can be much larger, and the fifth forces aren't going to be suppressed. This allows the chameleon, and hence the name chameleon for its ability to hide. This allows the chameleon to hide from our detectors. The fifth forces that we are looking for are suppressed in our environment because we are close to the Earth, because it is a more dense environment. Another example is the symmetron. So the symmetron has a screening mechanism that works differently. It undergoes a phase transition at some critical density rho c. For densities greater than, it has one minimum at phi equals 0, and so you would not observe any fifth forces because everywhere phi is a constant. But for environments where rho is less than rho c, the phase transition occurs, and so now the minimums occur at two values, same magnitude but opposite signs. And so now we can exhibit fifth forces. And so this is another example of a type of screening mechanism. So I briefly showed you the equations for the simple case of two parallel plates, so effectively 1D problem. You can solve them analytically. Here are the equations. I show you these with the intent of showing you that they are complicated. Here we've got Jacobi elliptic functions, and it doesn't get better. For the chameleon, there are approximate analytic solutions for things like spheres and cylinders, but no exact solutions. And so this is kind of arguably a problem as we have exchanged our ability to solve the equations for the nonlinearities, which gives us the screening mechanisms in a way. And so when it comes to exact or approximate analytic solutions, we're restricted to these highly symmetric cases, but real experiments are going to violate those symmetries. For example, here's a sketch of a atom interferometry experiment. The hole in the sphere you could assume to be small enough that the field doesn't really detect it, but the mirrors are going to influence it. And the vacuum chamber in reality probably isn't going to be spherical. These are things that have to be taken into account. And so realistically, you're going to have to use a numeric simulation in order to figure out what your field profile is actually doing. That is the one of the main motivations of this code. Rather than you having to start from scratch and write your own solver, you can just use this pre-existing code, stick in your existing experiment, and it'll give you the field profiles that you want. Um, Another reason against these shapes, not only can you not solve them, but the more complicated shapes that you can't solve for are probably going to give you better results, stronger fifth forces, so that your experiment is more sensitive. Uh, as I mentioned, my collaborator Andrius is also giving a talk, and he's going to touch upon how we use this software to optimize sources in atom interferometry experiments. So, what is a SELCIE? So, as I mentioned, these models they are interesting because their behavior changes depending on the environment that they're in. And so the software that I'm developing to solve them, I thought it appropriate to name them after the mythological creatures of SELCIE, given that they appear as seals in water. When they come onto land, they turn into humans. They both change depending on the environment. And so how the code works, it uses a combination of the finite element method solver, Phoenix, and meshing software, GMSH. So how the finite element method works and why we use it, um, with these types of scalar fields, they can be very steep. So if you have a region where you basically have a step function in density, you're going to have a very steep curve. And then when you get into your less dense region, it's going to plateau. And so it doesn't make sense to have an evenly spaced mesh because you're going to be wasting computational effort. Finite element method has the benefit of you can use meshes like this, where in the regions where you really want high precision, you can have really fine meshes. But then as you move away from those boundaries, it becomes coarser where you don't need the precision anymore. So how it actually works is it takes the Laplace equation and it allows you to solve it as a matrix multiplication equation. How it does this is every single vertex will have some value, and that will make up a matrix. And then we can express the continuous function as a sum, so the purple box, the sum over those vertex values with some basis functions. So these will be functions where it's like one at the vertex, zero at every other vertex, and there'll be some function between those two values. Um, and so by using that, we can take all of the mesh information and contain it inside of the matrix definition, so there's capital M. And so now our problem is just matrix multiplication. With the caveat of we need our function f to be linear, but we can kind of get around that by using a linearization method and then applying iterative procedure. So rather than solving the nonlinear equations, we can linearize it. Here's an example for the chameleon. We solve for the linearized phi around some guess phi of k, and then we use phi and phi of k to get our next value phi of k plus 1, and that's our next guess. And we repeat the procedure. And what you find is that as you iterate forward, your linearization becomes a better and better approximation as you approach the true solution. Here, omega is a parameter that lets you control the speed of the convergence. And then you terminate when the difference between successive values is below some tolerance. So to prove that I'm not selling you snake oil, those analytic solutions for the chameleon and the symmetron I showed you before, here is a comparison between what the code produces and the analytic solutions. Below, I've plotted the relative error on the left and the absolute error on the right. And as you can see, they agree. In fact, the only limitation here was how the tolerance that I allowed and the level of refinement on the mesh. For those who are allergic to code, don't worry. I've tried to make it very user friendly. So here is a complete example. If you copy and pasted this code into Python, you generate these two plots. Um, Here I'm also demonstrating the fact that you can assign functions as density profiles. So here the background density is a function of x. I really wanted to make it so that it's completely user dependent, not dependent. The shapes and the density profiles can be user defined. If you can, even if it's not physical, you could still in principle simulate it. And to illustrate this further, here's another example, some examples where you can generate some weird and wacky shapes and assign weird and wacky density profiles, and it's able to simulate it. So even if you have, say you have an experiment where you're able to control some, I don't know, like gas sphere, so it's not a discrete density cutoff, it's got some continuous density profile, and you're able to manipulate that. That is something that you can simulate with the code. And to illustrate it, just the freedom to make whatever shapes you want, I simulated what a chameleon would look, the chameleon profile of a chameleon would look like. I don't know how he got in there, but it looks good. For those experimentalists who have step files to keep track of the experiment, I'm currently working with experimentalists to simulate an atom interferometry experiment they're doing. And I'm working on the ability, it's going to come out hopefully soon, the ability to read a step file directly into the code. So here there's a component of their experiment. I was able to read this directly from the step file. So I hope this is a feature that experimentalists will appreciate. So as I mentioned in the title, one of the new features is time evolution. So I think this is really important because there have been many experiments trying to constrain these scalar fields. And I think the next sort of stage of these experiments is going to have to include time evolution in some way. So, for example, this experiment was able to use a rotating source to try and induce an oscillation. And by looking at the frequency of those oscillations of the source mass, of the detector mass, they were able to constrain the chameleon. And in fact, they were able to constrain a region of parameter space that hadn't been constrained by other experiments. So I think this is going to be, it's going to be very important to be able to simulate the effects of moving components on these field profiles. So for the sake of time, I'll just skim over this. You're able to solve using the forward or backward Euler method. The main method is the Crank-Nicholson because it's of higher order. Here I have some analytic solutions that we derived for constant density profiles. So on the left, this is for the chameleon where we have perfect vacuum and the field profile is able to evolve. On the right, we have an approximate solution for when the density is fixed at some value. And as you can see, the numeric time solver and the analytic solutions match very well. Again, for the symmetron, here the fixed density is at the critical density. And again, we get strong agreement between the analytic and the computational results. So we're now starting to look at systems where we're evolving the density as well. So here we have a sphere that has a varying density, and we're able to simulate the scalar radiation coming off of it. So nearly out of time. So for future work, we're looking at experiments where we can take advantage of time evolution. We're also looking at different scalar field models, like, for example, the dilaton. If you're interested in the work so far, these are the papers where we've been able to use SELCIE for various things from astrophysical, cosmological scales to tabletop experiments. Thank you for listening, and I look forward to the discussion session.